Hey everyone, and welcome. Today we're going to dive into 5 principles that are no joke, the absolute bedrock of clean, professional software design. We're talking about solid, so let's get right into it.
You know that feeling, right? You make what seems like a tiny, harmless change over here, and then suddenly a completely unrelated feature on the other side of the application just collapses. It's that classic house of cards, and it's a sign that the foundation of your code is a little shaky.
Well, solid is the answer to that problem. It's an acronym for 5 design principles that act like a blueprint for strong architecture. Following them helps us escape that tangled, fragile spaghetti code and start building apps that are solid, easy to change, and ready to scale. Okay, let's kick things off with the first letter, S. This stands for the single responsibility principle. And this one is so beautifully simple in concept, but it is incredibly powerful when you put it into practice. This is the golden rule, right here. Now, it doesn't mean a class can only have one method or do one tiny little thing. What it means is that all of its parts should be focused on one single job. If you find yourself changing a class because the database logic changed and also because the printing format changed, well, that class is doing too much. So a super common mistake is creating something like an invoice manager that tries to do it all. It calculates the total, it saves to the database, it prints the PDF. It becomes what we call a God class. The fix is to break it apart. You create an invoice calculator, an invoice repository, and an invoice printer. See? Now each class has just one single reason to ever be changed. And here's the magic. If your boss comes to you and says, hey, we need to change how invoices are printed, you just go into the invoice printer class. The invoice calculator? Totally safe, completely untouched. This drastically reduces risk and makes your life as a developer so much easier. All right, next up is O, which builds right on top of that solid foundation. This is the open/closed principle, and it's really all about a simple idea, adding new stuff without breaking the old stuff. Now, I know what you're thinking. Open but closed? That sounds like a total contradiction, doesn't it? But what it really means is that your code should be designed so you can add new functionality, that's the open for extension part, without ever having to go back and mess with the existing, tested, working code. That's the closed for modification part. So imagine you have a discount calculator. If you want to add a new premium customer discount, the bad way is to go back and add another if or else if statement to your original code. The right way, you create a contract, an interface, called something like iDiscount strategy. Now, any new discount type, premium discount, holiday discount, whatever, can just plug into the system. You're extending what the system can do without ever touching that original stable code. And the payoff here is just massive, especially for long-term projects. It means your core logic becomes incredibly stable. You can add feature after feature, year after year, and that core foundation of your application just stays solid as a rock. All right, on to L, the Liskov Substitution Principle. I know, this one sounds a bit academic, a little scary, but the core idea is actually pretty simple. It's all about making your code predictable. To put it simply, if you have a piece of code that works with a parent class, you should be able to swap in any of that parent's child classes, and everything should just keep working. No surprises, no weird behavior. The child has to be a perfect substitute for the parent. The classic example here is the best one. Let's say you have a base class called bird, and it has a fly method. Now, an ostrich is a bird, right? So we make ostrich a subclass of bird. But wait, ostriches can't fly. So if calling the fly method on an ostrich object throws an error, you've just broken the principle. The ostrich is not a perfect substitute for a bird if your program expects all birds to fly. That kind of surprise is exactly what leads to bugs. So why does this matter? Well, it builds trust into your system. It means you can use any subclass with confidence, knowing it won't suddenly misbehave or crash your application. It's all about creating reliable and predictable code. Next up, we've got I for the Interface Segregation Principle. The easiest way to think about this one is as the less is more principle. It's about keeping things lean, mean, and specific. The big idea here is that it's much better to have many small, specialized interfaces than one giant do-it-all interface. You should never, ever force a class to implement a method that it has no use for.
For example, it's a bad idea to create one giant I-animal interface that includes methods for fly, walk, and swim. Why? Because then when you create a dog class, you're forcing it to have a fly method, which makes no sense. The much cleaner solution is to create smaller interfaces, like iWalker and iSwimmer. A dog can implement both of those, but it never has to pretend it has wings. And the result of doing this? You get much cleaner, leaner classes that only contain methods they actually need. Your whole system becomes more intentional and easier to understand just by looking at which little interfaces a class decides to use. And finally, we've arrived at D, the Dependency Inversion Principle. Honestly, this might be the most important one of all for building truly flexible, loosely coupled systems that are a dream to test and maintain. Okay, I know that sounds really dense, but this is a total game changer. So let's break it down. High-level modules, that's your important business logic, like a notification system. Low-level modules, that's the nitty-gritty detail, like a specific email service that sends an email. The principle says your important logic should never be directly tied to a specific detail. Instead, they should both connect through a middleman, an abstraction, which is really just a fancy word for a contract, like an interface. So without this, your notification class is hardwired to the email service. If someone asks you to send an SMS instead, you have to rip open the notification class to change it. But the better way is to make the class depend only on an iMessage service interface. Now it doesn't know or care if it's an email, an SMS, or a carrier pigeon doing the work. It's completely decoupled and free. So the pattern is actually pretty simple. First, you define that contract, the interface. Second, your important high-level class says, I just need something that follows this contract. And third, your low-level detail class comes along and says, hey, I can fulfill that contract. This inverts the dependency, and that's what gives your system its flexibility. And that is solid in a nutshell. Let's do a super quick recap. S, one class, one job. O, add new things without changing old things. L, make sure child classes are perfect substitutes. I, use small, specific interfaces. And D, depend on contracts, not on concrete details. You know, when you put these side principles together, they help you create code that is just a joy to work with. It's maintainable, it's flexible, and it's robust. So the only question left is, when you look at your own projects tomorrow morning, which one of these powerful ideas are you going to try first?